All right, hello, welcome to another video. This video is going to be geared toward a calculus class. We're going to talk about how to find increase and decrease in intervals, as well as intervals of concavity for a trigonometric function. So let's get to it. F of x is equal to sine squared of x minus 2 cosine x along the interval negative pi to pi. So that interval is very important. So let's get started. All right, before I differentiate, I want to look at sine squared as being written a little different. That way you can actually see the chain rule being applied. So if I take that sine squared of x and I write it just a little bit different, it'll look like this. So now you can visualize this as being a composite function. Take the exponent 2, multiply it by the coefficient. So we have 2, and then rewrite the inside, which is sine. Decrease the power by 1, so 2 minus 1 is 1, and then differentiate the inside. The derivative of sine is cosine. Okay, now we want to go to that second term, minus 2 cosine x. So here we just want to take the derivative of cosine, which is negative sine, and then we'll take negative 2 times negative sine x and get plus 2 sine x. So let's clean this up a little bit, make it look a little nicer, and we'll have f prime of x is equal to 2 sine x times cosine x plus 2 sine x. Some of you guys may realize that 2 sine x times cosine x is sine of 2x, which is the double angle formula for sine. In this problem, because we want to set this equal to 0 to find our critical numbers, let's keep it written like this. Okay, so let's set the derivative equal to 0 to find our critical numbers. These two terms share or have a common factor of 2 sine x. So let's factor 2 sine x out of this equation. Okay, so now once you factor that 2 sine x out of both of these terms, you'll be left with 2 sine x times the quantity of cosine x plus 1, and that's the simple factoring of a GCF. All right, now we have this equation factored. Remember, once you have an equation factored and set equal to 0, to solve, you want to set each of these factors equal to 0 and solve those equations. So let's set our factors of 2 sine x and cosine x plus 1 equal to 0. The 2 sine x equals 0. All right, isolate sine. All you're going to do there is divide by 2. 0 divided by 2 is 0, so we could really just reduce this down to sine x equals 0. Okay, on the right side, we have cosine x plus 1 equals 0. What we need to do here is move the 1 over and get cosine x equals negative 1. So now we need to solve this. We need to think about where on the interval from negative pi to pi does sine x equal 0. Also, we need to look where on the interval from negative pi to pi does cosine x equal negative 1. All right, so here we have the first derivative. Of course, we have that listed. The factors of the first derivative, the critical numbers. Let's create our first derivative test sign chart. And to do that, we want to create our number line. Now, remember, we're only looking on the interval negative pi to pi. So being that our critical numbers are the endpoints of our interval, we only have 2 intervals to test, the interval from negative pi to 0 and from 0 to pi. So the way I like to do this sign chart analysis, the first derivative test, is create my number line. Over to the left, write my factors of my first derivative, which are 2 sine x cosine x plus 1. Create another line right below that. Under that line, write result. All right, show that we're working in 2 intervals. So we're going to create these little dashed lines. All right, and then within each interval, find a testing value. So think of any value between 0 and negative pi. Okay, so if you, again, remind yourself of the unit circle, I know the negative pi over 2 is within that interval, so I'm going to choose that as a testing point. In the interval 0 to pi, pi over 2 is in that interval, so I'm going to choose that as my testing point for that interval. So what I mean by these testing points, I want to take these and plug them into each of my factors and just see, does it make each of these factors positive or negative, and then finally find the result. And that's going to tell us where our function f of x is either increasing or decreasing. So if I plug in negative pi over 2 into 2 sine x, I don't necessarily care about what exact value that's going to be. I only care, is it positive or negative? Okay, so if you think sine at negative pi over 2 is -1, and so we have a negative value there. Now plug negative pi over 2 into cosine x plus 1. Cosine of negative pi over 2 is 0, so I have 0 plus 1, which is a positive. The result will be, okay, these are factors. So if I multiply a negative number times a positive number, that results in a negative number. Do the same exact thing in the other interval. Take pi over 2 and plug pi over 2 into both of these factors, and you'll get pi over 2 makes both factors positive, and therefore we have a positive result. And so that result line tells us where our function f of x is either increasing or decreasing. Okay, so this interval where we have a negative result, f of x is decreasing. All right, where we have a positive result, f of x is increasing. And there we go. So we know that f of x is decreasing along the interval negative pi to 0, changes direction at 0, and then starts increasing from 0 to pi. Okay? Now let's try to find the intervals of concavity. So let's go back up, look at the first derivative, and differentiate again. Okay, so I have the original function pulled up. I have the first derivative pulled up. Now from here to find the second derivative, there's a couple of different routes you can take. We mentioned earlier about an identity you can use. The 2 sine x cosine x can be rewritten as sine 2x. You can go ahead and apply that identity and then differentiate, or you could differentiate what you have here. So the product rule says you're going to take the first, which is 2 sine x, multiply it by the derivative of the second. So what is the derivative of cosine? Well, that's negative sine x. And then you want to add the second times the derivative of the first. So that's going to look like this, plus the second is cosine x, and then the derivative of 2 sine x is 2 cosine x. So there's the product rule. That's differentiating the term 2 sine x times cosine x. Now we want to differentiate the 2 sine x. And so if I differentiate this term, that's a basic term to differentiate. Again, the derivative of sine is cosine, and so that will be plus 2 cosine x. All right, I understand there's a lot going on your screen, so let's clean it up a little bit. Take a little bit of time. Let me know if something wasn't quite clear in differentiating this, but let's clean it up and make it look a little nicer, because remember, the goal in finding intervals of concavity would be finding possible inflection points, which is found by setting the second derivative equal to 0. So let's clean this up and we'll get this. F double prime, so the second derivative is equal to -2 sine squared x plus 2 cosine squared x plus 2 cosine x. Okay, so now to find our possible points of inflection, we want to set this equal to 0 and solve. Now this is a quadratic trigonometric function. I have made a video regarding how to solve these, so I'll link that in the description. Check that video out if you need a little extra help on solving quadratic trigonometric equations. But the idea is here, we want to apply one of our fundamental trigonometric identities to make this look a little nicer. What I mean by that is, notice I have a sine squared and a cosine squared, as well as a cosine. What I would like to do is rewrite this in terms of only one trig function being used. So either rewrite this with sines or cosines. And in this case, we need to rewrite this in terms of cosines, because we have this cosine here, we have a cosine squared, and then of course we have a sine squared. If you remember your Pythagorean identity, which is sine squared x plus cosine squared x equals 1, we can easily make a substitution for that sine squared x. Isolate sine squared x in your Pythagorean identity, and you'll get this. Sine squared x is equal to 1 minus cosine squared x. So take that 1 minus cosine squared x and substitute it in for sine squared x. Let's see what that looks like. Okay, so this is what that looks like. Now distribute your -2 and you'll get. All right, it looks a little nicer now, but we do have common terms. So let's combine our like terms and write this with our powers descending. So we'll have the following. This looks a little nicer. Now we have this trigonometric function in quadratic form. Notice the coefficients as well as the constants all are even. We can reduce them all by 2. So let's go ahead and do that. And we'll have this. This quadratic can be easily factored using whatever method of factoring quadratic expressions that you know. You will get these factors. All right, the factors would be 2 cosine x minus 1 times cosine x plus 1. Set these both equal to 0, and you'll get the factor 2 cosine x minus 1 equals 0 at -pi/3 and pi/3. And then the factor cosine x plus 1 equals 0 when x is -pi. So remember, we're only looking on the interval from -pi to +pi. So let's take these, and you'll see the sign chart on the next screen. All right, and so we have the sign chart here for the second derivative. Notice we broke it up into the possible inflection points. We tested each factor of the second derivative. We found our result, and our result tells us that the function f of x is concave down along the intervals -pi to -pi/3, as well as from +pi/3 to pi, and it's concave up along the interval from -pi/3 to +pi/3. Okay, so what we could do now is check ourselves in the calculator. All right, everything checks out. So I hope this video helped. If you have any questions, be sure to let me know in the comments. Otherwise, I'll see you in the next one.